So our first property has to do with swapping the bounds of integration. So notice on the left-hand side, we're integrating from a to b. Now, since we've been thinking about a as our left endpoint and b as our right endpoint, we're looking at the function along the x-axis moving from left to right. On the right-hand side, where we're integrating from the right endpoint to the left endpoint, we're thinking about moving in the opposite direction. So we're integrating not from left to right along the x-axis, but from right to left. Doing so introduces a negative symbol. So that says if you know the answer here, then the integral from b to a of f is simply its negative. The reason for this is that when you compute the width of your rectangles, on the right-hand side, we compute those using a minus b over n. This is the negative of what we normally use for delta x, which is b minus a over n. So on each of the terms, when we form the Riemann sum on the right-hand side, we introduce a negative that factors out, and that's where this formula comes from. Our second nice property talks about integrating over an interval of 0 width. So unsurprisingly, if you integrate a function where the upper and lower bounds are the same, you should get 0. The reason for this is delta x in this case is 0. So when you compute the Riemann sum, you're simply adding up a bunch of rectangles which have 0 width and therefore 0 area. No matter how many of them there are, you're always going to get 0. So our third property talks about what happens if you scale a function by a constant. This one's pretty easy to see directly from the Riemann sum. So first, when we write down the Riemann sum, we observe that each of the terms are multiplied by c. From our last video, we know that we can factor the c out of the sum, and now all we need to know is the limit laws. Since we have one function that has a limit as n goes to infinity, namely because it's a constant, and a second function that also has a limit because our function is integrable, that tells us that we can split this as the product of the two limits. So we recognize that the first term here, that's the integral of c times f of x from a to b, while this last term here is c multiplied by the integral of f of x from a to b. Our next property has to do with addition and subtraction of integrable functions. So if we have two functions, f and g, that are both integrable on the closed interval from a to b, something that would be nice to know is if we integrate their sum or their difference, that we get the sum or the difference of the integrals. So this tells us that if we have two functions that we know how to integrate, if we want to add them together or subtract them from one another, then integrate, that's the same as integrating each of the two functions independently, then adding or subtracting them. This one is also easy to see, straight from the limit definition. So when we plug our sample points, which happen to be the right endpoints, into our functions f and g, then add or subtract and multiply by delta x, then sum them all together and take the limit, we know from the last video that we can split the sum or the difference. And now, because we know both of these functions are integrable, we know each of their limits exist. So the limit laws tell us that we can simply split this as the sum of two limits. And each of these two limits are the integrals that we want. Our next property is how to integrate a constant. So there are two things to note here. One of them is if c is a positive number, then this should absolutely make total sense. If the integral measures the area underneath the curve, then c times b minus a is clearly the area of the rectangle defined by the constant function c. However, if c is negative, there's something interesting to note here. When c is negative, b minus a is a positive number, c is negative, the result is a negative number. This actually tells us that the integral measures more than just area. The integral also happens to measure the location of a region. Areas above the x-axis are always going to be positively signed. Areas below the x-axis will be negatively signed. Our next property tells us how we can break up the integral into multiple pieces. So the proof of this is beyond the scope of this class in general, but we can easily see a geometric argument for this whenever our function is positive. So if our function is above the x-axis on the interval from a to b, then the integral of that function from a to b measures the area of the region enclosed. So if we choose some value c, somewhere between a and b, then we get two regions. These two regions each have an area. We'll call them a1 and a2. If I want the integral from a to b of our function f, then clearly the area of the entire region in this picture should be the sum of the area labeled a1, the area a2. Well, but a1 is the integral from a to c of our function f, and the area a2 is the integral from c to b of our function f. Finally, we have a nice comparison property. So if we have two integrable functions, f and g, f is smaller than g on the interval from a to b, then the integral of f on a to b should be less than or equal to the integral of g on a to b. If you think about these as both being positive functions, then this should make sense. A taller function encloses a larger area than the shorter function. In general, you can see this from the Riemann sum. Since each of the points x1 through xn lie on the interval from a to b, we can replace f of xi for each I between 1 and n by g of xi. So having replaced f of x1 by g of x1, we've made this term larger. By replacing f of x2 by g of x2, we've made this term larger, and so on. Replacing f of xn with g of xn makes this term larger, so the sum of these larger terms is clearly larger than the sum of these smaller terms. Now we simply use the fact that limits preserve inequalities. There are two special cases here that are nice. Namely, we can give estimates for an integral based on lower and upper bounds on our function. So here we can use two applications of the theorem that we just proved. So on the one side, we have the constant function little m. That's definitely smaller than the function f. So the integral of this constant function, which is m times b minus a, that is smaller than the integral of our function f. Similarly, if we have the constant function capital M, which is larger than the function f, then the integral of capital M should be at least as large as the integral of f. Geometrically, this says if you're looking at a function, f, if you choose the smallest and the largest points of this function, if you use the closed interval method on this function, you can identify the maximum value and the minimum value of this function on the interval. The maximum value, which we call capital M, defines a rectangle. The right-hand inequality tells us that the area underneath our function f is no bigger than the area enclosed by the blue rectangle. Similarly, we can draw a rectangle in green corresponding to the minimum value, little m. The left-hand inequality tells us that the area bounded by the green rectangle, which has height lowercase m and width b minus a, is smaller than the area enclosed by our function, which is also evident from the picture. And that's all for this video.